Welcome everybody. In this set of videos, we're going to learn how to start solving some exponential and logarithmic equations. And there's different strategies, even for each type. So even for exponentials, there's a few different strategies we can use. For logs, there's a few different strategies we can use as well. So I'm just going to walk you through some of those in these videos here. So first, I want to start with our exponential equations. An exponential equation is an equation that contains a variable in the exponent. Okay, so you have some examples here that you can see on the page, and notice that your x is in the exponent instead now. There are different strategies for solving these style problems, and one strategy involves using this property, that if you have the same base raised to powers, then basically you can kind of get rid of the base, and those powers must also be equal. So as a very simple example, for instance, let's say you had 2 to the x equals 2 to the 3. Well, for these to actually be true, the exponents would have to also be the same. So to solve that, you're just setting your two exponents equal to each other, and we get our solution that way. So that's the property that we're using here. So your goal here is to try to make it so that the bases are the same. Okay, so that's our main goal using this strategy. So here I see a base of 2, and here I see a base of 16. Now, think of it a little bit like puzzles. If I think about that number 16, that one's kind of jumping out at me a little bit more. That, well, if I do, let's see, 2 times 2 is 4, times 3 is 8, times 2 times 2 is 4, times 2 is 8, times 2 again is 16. So 2 to the 4th is 16. So what I can do is rewrite this as 2 to the 3x minus 8 equals 2 to the 4th. Now you're having those same bases. So once you have the same bases here, and again, there's nothing else going on. It's just the left side equals the right side, and both of them have that same base for the exponential. Then you set those two exponents equal to each other. And now here we end up with a linear equation in this case, and we can just solve using our regular techniques. So 3x equals 12, divide both sides by 3, and I have x equals 4. Now you can still check by plugging your answer back into the original equation. I'm just going to do one check here just to show you that it still works. So I go back to my original equation. I replace my x with 4. Well, 3 times 4 is 12. 12 minus 8 is 2, and 2 to the 4th is 16. So you can still check your answers here using the regular techniques we always have when we solve equations. All right, let's do another one. So here I see a 27 and I see a 9. So this one's a little bit more complicated. I'm trying to think, okay, I can't make 27 into 9, right? That's 9 times 3, but that's not a power. It doesn't help me. We want to think about in terms of powers here. We're doing exponents. But I do notice that they both are multiples of 3, right? 9 is 3 times 3, and 27 is 3 times 3 times 3. So they all have this sort of base factor of 3 here. So I think I'm going to use a base of 3 in this case. Okay. So like I said, 9 is equal to 3 squared. So for this side here, 9 becomes 3 squared to the x minus 1. And then 27 is the same thing as 3 cubed, 3 times 3 times 3. So this side becomes 3, let me rewrite this better. So 3 cubed to the x plus 3, and then 3 squared to the x minus 1. Now that still looks pretty messy, so we're going to clean it up a little bit. You do want to know we do have an exponent rule that when you're we have an exponent and you have a power to a power, you can actually multiply those exponents together. So I'm actually going to distribute here and write this as 3 to the 3x plus 9. Then over here, I'm going to distribute that to 3 to the 2x minus 2. And now I see I have the same base equal to each other, so I can go ahead and set those two parts equal and solve. So I have 3x plus 9 equals 2x minus 2. Subtract 2x from both sides. I'm going to subtract 9 from both sides, and I end up with x equals negative 11. Okay. Now you can definitely still plug this in and check. It does work. So if I plug in negative 11 here, I have 27 to the negative 8 power. If I plug in negative 11, I have 9 to the negative 12th power. Now, because I'm just doing a check, this could be a good time to use your calculator, so I don't have to do too much work. So I would end up with, let's see, we said 27 to the negative 8 power, and that will give me, let's see, about 3.54 e to the negative 12. So when you see that e to the negative 12, it actually means to take that decimal point and move it 12 spots to the left. But again, I'm just doing a check, so I'm not too worried about that. And then when I do the 9, it was 9 to the negative 12 power, and I see that I get that same result. So I'm just plugging my answer back in here, using my calculator to help because it's just a check, and I do see that both sides are still the same. So that's one strategy we can use for solving exponentials. Now, obviously not every exponential can be rewritten such that each side has the same base, and things don't always work out that nicely. And then you see something like 4 to the x equals 15 is a perfect example. 4 is just 2 times 2, so the base I could use is 2 there. 15 does not have a base of 2, it just doesn't work, so that same strategy is not going to help here. So we have a second strategy that we can use for exponentials, and this strategy is actually used a lot. It really is. It's used a lot, particularly in more complicated equations as well. And that is when you take the log of each side. So remember, when we do the same thing to both sides of an equation, we're still keeping it balanced. We're not changing anything there. So we're going to take the log of both sides. So we're not changing the problem. But it's going to allow us to basically take that exponent and pull it out front. Remember that power rule that we worked on in a few videos ago? When we take the log of both sides, we're able to take that x and pull it out front. So it's just a lot easier for us to solve now. Now, you can actually use any log you want. It doesn't have to be the natural log. Typically, you would use either the natural log or the common log because that's what your calculator can help you out with. We tend to use the natural log most often, though. In upper mathematics, that tends to be the go-to base. So here, I looked. There's no way for me to rewrite it so I have the same base on each side. So the technique I'm going to use to solve is to take the natural log of both sides. So I take the natural log of the left side and the natural log of the right side. Now, you don't really have to use parentheses. I just find it a little bit easier to read. And what you want to remember is you do have that power rule. So that's going to let that x come out front here. So you have x times the natural log of 4 equals the natural log of 15. Please note here, this is an L and an N, not an I, not an E. A lot of times students make that mistake when they're typing natural log, particularly in my math lab. It is a lowercase L and an N. So now we want to solve for x. This is a little bit weird, but ln4 is actually just a number. Your calculator can give you a decimal approximation. So think about how you would solve a regular problem, right? If I had like 2x equals 4, you would tell me to divide that 2 on both sides. Well, I'm going to do that same strategy here. I'm going to divide both sides by the natural log of 4. And I have my answer. So natural log of 15 over natural log of 4. Now that's the exact answer in log form. There's nothing else you can do to simplify there. If you do want it in the calculator form, though, an approximation, you're just going to go to your calculator. You're going to type in natural log of 15, and then you do want to close the parentheses, so that looks like this. And then you're going to divide that by the natural log of 4, and again, close the parentheses, and then hit enter. So you get about 1.95 here for your answer. So the exact answer, the approximate answer. I do want you to be careful with your calculator. So notice how I have that log written twice, like I do here. If you write log and then you do 15 divided by 4 kind of in one group and not paying attention, you will get the wrong answer. So when you have logs like this, you can't just simplify the 15 and the 4 or get rid of one of those log notations. It's wrong. So be really careful because these are not the same thing. All right, let's do another one. Now here, you actually can still take the natural log of both sides if you want to. You're going to get the correct answer. But because I have base 10, this could probably be a better one to use the common log. So I'll take the common log of both sides. And then that's going to allow me to pull that x out front. And actually, remember that log of 10 is just 1. So when we take that out front, this log and 10 are going to just cancel out because it's the same base with the same base for the exponent as well. So these pieces really just cancel here. You do have that factor of 1, though. When we're multiplying, it's not going to matter. So 1 times x is still x. And I have that value of 120 here. And again, I could take out my calculator, log of, sorry, 120,000. And when I plug that all in, I get about 5 points, we'll say 0.08. So I have my exact form, and then I also have my approximation here. A lot of times we do like to leave the answer in the exact form, unless we're doing an application, then it is helpful to have the approximation many times.